You've no doubt heard of functions before, and you probably even can piece together some kind of definition of it. We're going to formally define them and then talk about some properties that certain functions have. So it turns out that a function is really just a relation. It's a specific type of relation. So we have two sets, A and B. Our function f is the relation from A to B with the property that every element in A is the first coordinate in exactly one ordered pair in our relation f. So since f is a relation, we can talk about the domain of our function f. And remember, the domain of a relation is the set of all of the elements that appear as the first element in the ordered pairs that make up the relation. So since we have that every element in A is going to be the first coordinate of exactly one of our ordered pairs in our relation, then the set A is actually the domain of our function. Likewise, we call B the codomain of f. So the function that we're mapping to, those elements that are going to appear as the second coordinates, whether or not they actually appear, the set that they're being pulled from, that whole set is called the codomain. So if we have some ordered pair in our function f, so say AB is one of the ordered pairs in the relation or our function f, we write it as B equals f of A. No doubt you've seen this notation before as well. Now, what you may not have heard is B is referred to as the image of A under the function f. So there's other times too that instead of calling f a function, we say it's a map of A into B. Sometimes we say that like f itself is a mapping. So words that get tossed around with functions when we're looking at them in terms of being relations and sets like this. Also, the concept of range comes up. So in the relation, we had the range as all of the elements that actually showed up as the second element in an ordered pair of our relation. So the range of a function is the same thing. It's the set of all elements in B such that that element is an image under f of some element in A. Or we can just say it's the set of all f of x, given that x is an A. Now, if A is a finite set, then the function is a finite set of ordered pairs. And the number of elements in f is actually the number of elements in A. Those two things are equal. Now, when we're talking about two functions being equal, say I have a function f from A to B and g from A to B, we can say that those two are equal if f of A equals g of A for every element in A. So it has to be equal and it has to be mapping to the same set. Now let's take a look at an example. So I have a set that consists of the elements 1, 2, and 3, and a second set B that consists of the elements W, X, Y, and Z. Now, if I define a relation F1 as being the set of ordered pairs 1y, 2w, and 3y, this is a function from A to B, so we can write it using our function notation. Now, it's a function because the elements 1, 2, and 3 that are my set A each appear exactly once in my relation. So now, if I take a look at relation F2 here, I have a set of ordered pairs 1x, 2z, 3y, and 2x. Now 2 shows up as the first coordinate in 2 of these ordered pairs. And that means that F2, while it is a relation, is not a function. Now let's take a look at relation F3. It consists of the ordered pairs 1z and 3x. Now notice that the element 2, which is an element in A, is not the first element in any of the ordered pairs in the relation F3. That means that F3 is not a function from A to B because the domain of this relation does not equal the set A. On the other hand, if I say that I'm looking at the set A minus the element 2, f3 is a function from that set, A minus the element 2, to the set B. You've probably seen this depiction of a function before where we can represent it with a diagram. So we put our set A in a circle and we put our set B in a circle, and then we draw an arrow in between the elements of A and the elements of B to show where the function is mapping each one of the elements to. In order to be a function in this case, we need every element in A to have exactly one arrow coming from it. Now, in calculus, you tossed around the idea of functions as being like f of x equals x squared. And we said that f of x is a function when we were talking in terms of calculus. Now, what this is, the function f is a mapping from the real numbers to the real numbers. So a and b are both the real numbers. And we say that f of x is a function, but really what it is the image of a real number under a function. F itself is the function, and f is actually the set of ordered pairs x squared with the element and its mapping paired together for all x in the real numbers. So elements that are actually in this function is like 2, 4 or -3, 9. Those actually belong to the function. Now, when we take a look at the set of all of the ordered pairs, x squared for all x in the real numbers, then if we plot those points on the plane, what we have is the graph of the function. So in this case, our graph is a parabola, and we have the function f mapping the real numbers to the real numbers, and it's defined by f of x equals x squared. So we can think of it as a rule that associates some number with its square for all real numbers. Now, if we take some subset of A, call it C, the image, we can write it as f of C under the function f, is defined to be the set of all f of x such that x is in C. So we know that f of C is going to be some subset of B for every subset C of A. And in fact, if C equals A, then f of C is going to equal f of A, and that is actually the range of f. So we can use this function notation and put a set in the argument rather than just a single element. And when we put a set in the element, what we are referring to is this set with all of the elements that are in the set in itself. That was a lot of words of set, but hopefully that makes sense, especially with the writing there too. So let's take a look at an example. So we have the set A has the elements A, B, C, D, E, and the set B that has the elements 1, 2, 3, 4, 5, 6. Now, the function f here with the ordered pairs, A3, B5, C2, D3, and E6 is a function from A to B because all of the elements of A are represented exactly once as a first coordinate in those ordered pairs. Now, if I take a look at the subset, say C1 being ABC, so subset of A, ABC, if I take a look at the function of that set, I'm looking at the image of that subset of A, what I get is everything that's a second coordinate with A, B, and C. So 3 is in there, 5 is in there, and 2 is in there. And I would list them in order, 2, 3, 5. And similarly, I can do the same thing for C2 being AD, C3 being E, C4 being A, all of A. So we can see those worked out. Now, with functions, you've also seen inverse functions. So if we have a function from A to B, and we have some element, say lowercase b, in B, the inverse image, or f inverse of B, is defined to be the set of all the elements in A such that the function mapped that element in A to the B that I'm interested in. So we know that the inverse image of an element of B is going to be some subset of A for every element in B. So we also can put sets in the arguments for the inverse image as well, the same way we could for the function itself. So if I have a subset D of B, then the inverse image of D is going to, again, be some subset of A, being all of the elements in A, such that f of A is an element in D. So we also can see that if we take the inverse image of B, we need to get A. So again, here's back to my example of A being A, B, C, D, E, and B being 1, 2, 3, 4, 5, 6, and F being the relation that is a function defined as the set of ordered pairs A3, B5, C2, D3, and E6. Then we can look at the inverse image of, say, 3. So I'm looking for everywhere that 3 is the second coordinate. Well, that happens when the first coordinate is A and when the first coordinate is D. So the set AD is the inverse image of 3. Likewise, I can do this when I'm looking for both 1 and 3. 1 doesn't appear, so A and D is again that set. I could look for the inverse image of something like 4. 4 doesn't appear, so the inverse image of 4 is the empty set. And if I take the inverse image of all of B, then I see that I get all of A. So one property that functions can have that can be really descriptive of it is it could be one-to-one or injective. So we use those words interchangeably. So a function f from a set A to a set B is called one-to-one or injective if every two distinct elements of A have distinct images in B. Now, in symbols, what we might do is say we've got x and y are elements in A, and x is not equal to y. Well, then f of x does not equal f of y. That's what we're saying for some function from A to B. Now, if a function is not one-to-one, then there exist distinct elements, say w and z, in A, such that f of w equals f of z. Let's take a look at an example. So have sets A equal to a set having the elements A, B, C, D, B having the elements R, S, T, U, V, and C having the elements X, Y, and Z. Then I have this function f1 that maps A to S, B to U, C to V, and D to R. This is a one-to-one function from A to B since distinct elements of A have distinct images in B. All right, so since this is such a small function, we can actually just spot check it, look at it, and know, because we can exhaustively look at it all. Now, let's take a look at f2, again, a small function that we can exhaustively examine. So this function maps A to S, B to T, C to S, and D to U. Now, since A and C both map to S, that means that they have the same image, and it is not a one-to-one function. Also, since there are fewer elements in C than there are in A or in B, there is no one-to-one function from A to C. And we can generalize that idea. So suppose we have some function f from A to B. It's one-to-one. A and B are finite sets. Right? Since every two elements in A have to have distinct images in B, that means that there have to be at least as many elements in B as there are in A. So what that means is the size of A is less than or equal to the size of B. Right? So one of the ways that we define one-to-one in like an equivalent way is we say we have a function f from a to b, and we say it's one-to-one if whenever f of x equals f of y, where x and y are in a, then x equals y. So let's take a look at an example where we can do a proof using that formulation. So we have a function f from the real numbers to the real numbers, and we are going to define it as f of x equals 3x minus 5. And we want to show that it's one-to-one. So using our alternative formulation that we just stated, we get to assume that f of a equals f of b, where a and b are some real numbers. We don't know if they're equal or not. They're just some real numbers. So we set f of a equal to f of b. So 3a minus 5 equals 3b minus 5. Well, we can simplify this by adding 5 to both sides and get 3a equals 3b. And we can simplify it further by dividing by 3, and we'll get a equals b. So it happens that when f of a equals f of b, then a equals b. So f is one-to-one by that alternative formulation of our definition that we gave. Now, here's an example. We want to determine whether this function from the real numbers to the real numbers, given by f of x equals x squared minus 3x minus 2, is one-to-one. So we can look at it, and you might be thinking, well, that looks like a parabola, so it's not going to be one-to-one because there's going to be two x values that I can put in that'll give the same y value out, because that's just what parabolas look like. And that's good if that's your intuition, all right? So we know that we're not proving that this is one-to-one. We know that instead what we're doing is we need to give some example of two x values that result in the same y value. So 0 and 3, when they're substituted in for x, both give an image or a y value or an f of x value of -2. So we know by this example that there exist two distinct x values that actually result in the same image, and therefore f is not one-to-one. Now, another property that functions can have is they can be onto or surjective. Again, we use these words interchangeably. So a function is onto or surjective if every element in the codomain of B is the image of some element of A. So that really is saying that f of A equals B. So let's take a look at an example. I have A equals the set 1, 2, 3. B equals the set x, y, z, w. Now, the function f1 from A to B, defined by the set of ordered pairs 1y, 2w, 3y, is a function, but it's not onto because there are no elements in A that map to x or z. So both x and z are missing from the image of A. So similar to how we could make an argument about the size of sets with the one-to-one or injective, we can do the same thing for surjective or onto. So if A and B are finite sets and f from A to B, so some function f from A to B, is a surjective function, then the size of B has to be less than or equal to the size of A. So again, let's take a look at an example where we have our set 1, 2, 3 as A and our set B, x, y, z, w as our set B. So we're going to take a look at a function instead of going from A to B, from B to A. So G is going to be a function from B to A. G is going to be defined as the set of ordered pairs x3, y1, z3, w2. Now, this is surjective because every element in A appears as a second element in my function G. Here's an example where we want to prove that something is onto. So we have a function f mapping the real numbers to the real numbers defined by our function f of x equals 3x minus 5. Now we want to show that f is onto. So what we need to do that, for all real numbers, we need a real number such that f of x equals that real number. So we're going to be thinking, this is kind of like our in preparation for our proof. So we're thinking what we really need is 3x minus 5 equals r, where r is just any generic real number. Well, if we solve for x to figure out what maybe that needs to be, then x is going to equal r plus 5 divided by 3. So I can do this for any real number r. Those are legal moves. I'll never be dividing by 0 or anything like that. So that's a legitimate value that I can take for x. It's definitely a real number. So now that I've done that like pre-processing, then I can jump into the proof. So I'm going to let r be a real number, any real number. Then I need to show that there exists x that's a real number such that f of x equals r. Well, I've done the prep work to know that I need to choose x equals r plus 5 divided by 3. So we're going to choose that. Then x is a real number and f of x equals f of the quantity r plus 5 divided by 3. Well, 3 times the quantity r plus 5 divided by 3 minus 5 results in just r. So I have f of x equals r for that specific real number. And consequently, my function is onto or surjective. Now, if a function is one-to-one and onto, then we call it bijective or a one-to-one correspondence. All right. So bijective is because it's injective and surjective. One-to-one correspondence is this idea of it's one-to-one and it's onto, so everything corresponds to something. All right. So some properties of being bijective. If a function is bijective and the a and b sets are finite sets, then the size of the two finite sets are equal to each other. Now, if a and b are finite sets and their size is the same, then there exists a bijective function from a to b. Also, a bijective function from a set A to a set B creates a pairing of the elements of A with the elements of B. You'll hear that language as well. So let's take a look at an example. So we've got a set A consisting of the elements A, B, and C, and a set B consisting of the elements X, Y, and Z. Now, the bijective function from A to B, we have 6 possible versions of that. So there are 6 bijective functions from A to B. And it's not anything special about A and B here. It's really any 3-element set and any other 3-element set. If I take a function from one to the other, there's going to be 6 bijective functions. So let's generalize that and make it a theorem. So if I have finite sets, A and B, the size of the sets are equal, and say they equal the size n, then there are n factorial bijective functions from A to B. So let's take a look at how this plays out. So A consists of n elements, say a sub 1 through a sub n. Any bijective function is going to be mapping each one of those to some element in B. And the second coordinate is going to belong to something in B. Now, thinking about what I can map, what I can pair up with a sub 1 to be the image of a sub 1 under F, well, there's n possibilities, b sub 1 to b sub n. Well, I'll use one there, and then I'll move on to finding the image of a sub 2 under F. Well, I've used one of the n possibilities, so there's n minus 1 possible images remaining for a sub 2. And then I can continue, and I keep on continuing until I get to the point where I'm looking for the image of a sub n, and there's only one remaining possibility. So when I do that, it looks like I have n possibilities times n minus 1 possibilities times n minus 2 all the way down to 1, and that is just n factorial. So it turns out that if I have two sets, A and B, finite non-empty sets, equal cardinalities or equal sizes, and I have f as a function from A to B, then it turns out that f is 1 to 1 if and only if f is onto. So the function from A to B is either bijective or it is neither 1 to 1 nor onto. So there's a specific function that is bijective and super useful at times. It's called the identity function. And what it does is it maps one set to itself, and it does so by mapping each element in that set to itself. So the image of an element equals itself. Now we use I sub A as the notation for this special function, and it's called the identity function. So here's an example. I've got a set S consisting of the elements 1, 2, 3. The identity function on S is going to be 1, 1, 2, 2, 3, 3. And that's going to be the case for any identity function. It's going to look like that for any set. So let's take a look at an example where we want to show that something's bijective. So we're going to take a look at a function from the real numbers minus the element 2 to the real numbers minus the element 3. That's defined by f of x equals 3x divided by the quantity x minus 2. Now, since the domain and codomain are not finite sets, that means that we need to show that f is both 1 to 1 and onto to show that it's bijective. So let's show that it's 1 to 1 to begin with. So we're going to assume that f of a equals f of b, where a and b are some real numbers, and they're real numbers that don't equal 2. So we have 3a divided by the quantity a minus 2 equals 3b divided by the quantity b minus 2. Now, if we multiply both sides by a minus 2 times b minus 2 to get a common denominator situation, clear out our denominators, we're going to end up with 3a times the quantity b minus 2 equal to 3b times the quantity a minus 2. Now we can simplify that and we'll get 3ab minus 6a equals 3ab minus 6b. So we can subtract 3ab from both sides and we get to the point where we have minus 6a equals minus 6b. Dividing by negative 6 gives us a equals b. So we have that our function is 1 to 1. Now, since our sets, again, are not finite, we can't just say, since it's 1 to 1 finite sets, then it has to be onto as well. We have to, in fact, show that it is onto. So we're going to take some element r in the real numbers without 3, so some element in our codomain, and we need to show that there exists some real number minus 2, so some element in our domain such that f of x equals r. So we're going to do the prep work on the side the same way that we did in our previous example of showing that something was onto. And once we do that, then we're going to see that we want to choose x equals 2r divided by the quantity r minus 3. Now we're allowed to divide by r minus 3 because remember, r can be any real number except for 3. So we won't be dividing by 0 here. So substituting 2r divided by the quantity r minus 3 in for our function for x, we get everything simplifying down to be r. So we have f of x actually equals r. And because of that, f is onto. So since f is 1 to 1 and onto, f is bijective.